So thank you. We're here for the annual PH lecture. The PH lecture was endowed by Paul Hertlandy and his family, and Paul joins us every year on this occasion. Paul is an alumni member of the Smithsonian National Board. He was also well known, or perhaps notorious, as the poet laureate of the National Board. And he was for a number of years, he was the liaison between the National Board and SAO, and that's what brought us together. The family established this lecture to encourage and celebrate outstanding young scientists, and that's what we're doing here today. And a number of very significant folks have been previous PH lecturers. Sean Andrews, I saw Alexi earlier, yes, and Karen Oberg is here. Yes, so, and today we're graced by Smadar Naoz. So let me introduce Dr. Naoz. She's a native of Israel, grew up in Jerusalem, and was educated, got a BS and MS in physics, and in 2010 she got a PhD in physics and astrophysics at Tel Aviv University. Between graduate school and here at the CFA, she was at Northwestern University, at the new center there, and she's accepted and will shortly take up a faculty position at UCLA. So with that, I'll hand the floor over to Smadar, and she'll talk about the origin of retrograde hot Jupiters. Thank you.
Thank you, and thank you very much for the award. I'm very honored to get it. And I want to tell you a little bit about exoplanets. So extrasolar planets is a very excited field to work in. There's a growing flow of new observations that keep on challenging old theories and notions and promoting new ideas. Now, it seems that we observe exoplanets in a large variety of properties. They vary in their mass. We observe exoplanets from few Earth mass to tens of Jupiter mass. They vary in their distance from their star. Some exoplanets are orbiting their star once a day, and some takes several years to orbit their star. They vary in their eccentricity, in their multiplicity. It's a whole zoo out there. And we have yet to observe a system like our own solar system. And indeed, there are many observational biases for it, but just the mere diversity of these systems it's an interesting point by itself. Today, I'm going to focus on hot Jupiters. These are Jupiter-sized planets that are found to be in a very, very close proximity to their host star. And by very close, I mean a day orbit. Just for comparison, our innermost planet in our own solar system, Mercury, orbits our sun once every 3 months. So just imagine this huge, giant planet orbiting its star once a day. But even more surprising is that many of these hot Jupiters are in fact misaligned with respect to their stellar spin axis. So a system like this I would call aligned because the planet is orbiting in the same direction as the star spins, and it's roughly in its equatorial plane. But many systems are in fact misaligned, so the orbit is tilted with respect to the stellar spin, and some are even retrograde, so the orbit is going in the opposite direction. But why is that a problem? Maybe this is simply the way that planets are formed. So it's a problem because of the way that we think that planets are formed. So we have this idea. We start with some gas clouds that contract due to its own gravity, and it's formed a star with a disk. And if we had some initial asymmetry in the system, that sets the angular momentum of the system. So we have an angular momentum here that controls the sun and the star and the disk. So planets are forming in the disk, they're moving around, the disk is moving in the same direction as the star spins, but we should have planets that are orbiting in the same direction as the star spins. And it works very well in our solar system, where all the planets are orbiting around in the same direction as our sun rotates around itself, and all roughly in the same plane. And I'm saying roughly because it's up to 7 degrees. But what is 7 degrees among friends when we talk about 180 degrees? So this is the problem. We think that we need to form these planets, these Jupiter-sized planets, far away from the star, so where we have ices and gases. So we're forming them there. And then we need to bring them very close to their star and flip them in the same time. So I'm going to show you a new mechanism that not only explains how I can form these, how can I bring these planets so close to their host star, but also naturally explains how I can flip them in the same time. And in this mechanism, we have another perturber in the system, and it can be anything you want. It can be a planet, a brown dwarf, a star, and it creates gravitational perturbations that make the soon-to-be hot Jupiter planet more and more inclined, and even flip it, and it can make it more eccentric. If the orbit is very eccentric, it spends a long time around the star, tides work, tides play a role, and they can shrink the orbit. So we get a hot Jupiter flipped planet. But why do we care? Well, we care because we're selfish. Well, of course, it's an interesting problem, but we're also very selfish. So we want to understand Earth or Earth-like systems. And observations of hot Jupiters emphasize the idea that planets move around. They don't stay put in their birthplace. They move. And hot Jupiters show the largest movement of them all. They move in about 2 orders of magnitude, from approximately 5 AU to 0.02 AU. So this is a huge migration. And this means that there is an arsenal of mechanisms that at work here, dynamical or everything, that makes this work, that bring the planets very close. So if we can understand those dynamical processes that take place in a solar system, for the example, the great example that has this great move, maybe we can understand dynamical processes as a whole and understand what affect solar systems. Before I'll start, I want to say a word about my collaborators. So the basis for this work I have done at Northwestern, and they have a great center there called Sierra, and Fred Rassio is there, Yoram Lithwick is there. I'm sure they don't need a lot of introductions. Will Farr was a postdoc, we overlapped there. He's now a faculty in UK, Birmingham, UK, the opposite way. And Jean de Sadier, he was an undergrad back then, working with us. He's now finishing his PhD in Oxford, UK, and he will move to be a postdoc in the Technion, Israel. I'm also going to talk about work that I've done here, and I have collaborators here too. And I first and foremost want to mention Gonzie Li. She's a graduate student. She's over there, and she did an amazing job that I'm going to talk about. I also collaborated with Avi Loeb, who I'm sure I don't need to make any introduction to Avi, or to Matt Holman, which I also collaborated with, and Ben Sakaxis, who used to be a postdoc here, and now he's a postdoc at the IIS. In the luncheon, I talked about some work that I also collaborated with John Johnson, but it's not a part of everything that I'm going to talk about now. Okay, so the outline of my talk is that first I'll give some observational motivations, and then, of course, whenever we have interesting observations, we have many different mechanisms that try to explain it. I'm going to cherry pick some of them, because then I'm going to just talk 2 hours on other people's work, and I don't want to do it. So the mechanism that I've described in the beginning is known throughout the literature as the Kozai mechanism. And I'm going to show you that there is something wrong with a nominal Kozai mechanism, and once we fix it, everything comes forth. And it's really easy to understand what's going on. Then I'll ask some questions. There will be frequently asked questions. Some questions that I ask myself, some questions that you may ask me. And feel free to interrupt me during the talk. So observation. When I started giving these talks, I used to update this slide. And then I gave up and put larger than. And then I even gave up on this and put that. So this is from February. Kepler team had done wonderful things. And just almost a little bit more than 2 months ago, they have verified, they had about 700 and something planets that they verified in terms of multiplicity. So they see they have indications of many transits, and they say this must be, these must be planets. So the takeaway message of this slide is there are so many planets out there that we observe, and we just need some time to try and understand more and more what is going on. Now, I said it's a whole zoo out there, so this is part of the zoo. This is mass times the sine of the inclination between me as an observer to the system as a function of the semi-major axis ratio. The color code is eccentricity. And this is only part of it. This is up to 10 AU, but it extends much more. And I want to draw your attention to this. So this is some sort of a pileup of hot Jupiters. For me, I will call every planet which is about a Jupiter mass. I don't really care if it's a little bit less or a little bit more of a Jupiter. And below 0.1 AU, I will call it a hot Jupiter. I don't really care. I do want to note that if you look at this plot only on radial velocity data, this pileup is not so prominent. So this is an interesting, but beyond the scope of this talk right now. Now, I also talked about the spin-orbit angle. So this is what we observe. And we have some experts here in the audience. And yes, Josh, I mean you. So this is what we see. We have a star that spins. And as the star spins, this approaches me, this recedes me. So this looks more blue, and this is redshift away. If I observe at least one line during a transit, then the planet blocks first the blue part, and then it can block the red part. So I have some handle on what is the angle between the spin of the star and the normal to the orbit. But it's only the projected angle, because I don't know if the star is tilted with respect to the observer. I can only know if it's directly lie on toward me or away from me, because then there's no signal. So this is the projected angle that we observe, and this is what observations show. So here I've plotted the distribution of the spin orbit, the projected spin orbit angle, and I've cut this. I have clipped this bin. So this bin goes all the way to approximately there. And I clipped that because I want us to look at the misaligned guys. Now, it's about 50-50, approximately. 50 are aligned and 50 are misaligned, roughly. And if you look at this is pretty amazing. These guys, they look almost uniform, the misaligned guys. It looks like that I need not only to have some efficient mechanism, to make misalignment, I need it to be very efficient. So I need to produce something that it's close to uniform, at least in the misalignment regime. And I'm going to show you that we have something similar. Okay, so I said that there are lots of alternative models, and roughly, as I talked today in the luncheon, roughly we can divide them into two. One is dynamical origin, and the other is disk migration with flipping the star or the disk later. And just going to say I can divide it to something like planet-planet scattering. I'll explain what it is. Perturbation by another companion. This is very close to what I'm going to describe, so I'm going to leave comparisons to this to the end. And if disk migration rules, then we can either later flip the star or flip the disk. And this just to tell you, this is amazing. This field has produced so many interesting papers and ideas, and I underlined all the CFA connection, and I'm sure that I've missed some. So there is an interesting thing here, and I'm just going to really cherry pick a very biased review of what is existing in the literature. So, planet-planet scattering. The idea is that we scatter planets just like billiard balls, but instead of actually touching each other, it's gravitationally. And the end result from this is usually, typically not always, one planet is escaping, and is escaping the system, and we have one eccentric planet and one inclined planet. And here is a result of the spin orbit. This is a proxy for the spin orbit angle by Nagasawa et al. So it's a very popular. Actually, I need, I guess, to underline this because Matthew Payne was also collaborating on this, so he's here. Anyway, as you can see, if this is the distribution of a spin orbit angle, it doesn't look like the observation, or it doesn't look even uniform. So and we're going to quantify this more later. All right, so this is one mechanism that we have. We can also flip the star. So Josh Wynn had a very nice insight, and he said, well, I see a correlation between the projected obliquity, the spin-orbit angle, and the effective temperature of the star. And here we have that stars that are cold typically have very low obliquity, so they're more aligned with their planets. And stars that are warm can be all over the place. And he said, well, you know, very cold stars have large convective envelopes, and small and very hot stars have small convective envelopes. And his idea was, well, you start with some large initial obliquity, and then those large convective envelopes realign. So you grab and you tidally torque the outer shell of the star, and you realign the outer shell of the star. So this was his idea, and you do see this correlation, so it's interesting. We can also flip the disk. So this is Konstantin's idea, and he said, and it's not really flipping the disk, but flipping the disk is much better title here. So the idea here is here is the star, this is the protoplanetary disk, and we have some companion. And what the companion does, it simply makes the disk process, so we have precession of the nodes, and it appears to be in retrograde with compare to the spin orbit with the spin axis. We can also there is another way to flip the disk. Again, actually not flipping the disk, but come on, flip the disk is so much better title. And this idea, they said, well, you know, disks not come out of nowhere, and you have, in fact, disks are accumulating. They not just appear from thin air. So you have an envelope of gas, and this disk continue to accrete material. And it accretes material in all kind of directions of angular momenta. And therefore, you get warped disks. So what these guys were able to get, they were able to get very inclined planets, but away from their star. So it's interesting. And there is a reason, of course, why I'm mentioning this, because this may be a possible way to create high inclined, far away planets, which will be of interest to me. So everything is self-serving, of course. Okay, so enough with what other people have done. Let's move on. So as I said, the mechanisms that I've described is known throughout the literature as Kozai. And in fact, there were many works that have talked about how the Kozai mechanism can be applied to exoplanets, and also how the Kozai mechanism can be applied everywhere. And there were very interesting papers. And in fact, I think that Matt Holman was the first who ever applied the Kozai mechanisms to exoplanets. Correct me if I'm wrong. I think it was the first application of the Kozai mechanism, which was pretty amazing. And looking at all these very interesting works, we thought, well, maybe it deserves another look. And this is what we did. So in order to explain what the Kozai mechanism is, I need to define a new angle. So far we talked about this angle, the angle between the stellar spin and the normal to the orbit. Now, I want to leave aside the stellar spin for one moment, or a few moments. We will get back to it soon. And let's assume that we have another body in the system. So here I have the star, the planet, and let's assume that I have somewhere another guy. If I have another guy, the total angular momentum of the system, of everything together, is not necessarily aligned with either the stellar spin or the normal to the orbit. It can be somewhere else. So I'm going to define a new angle. It's the inclination angle between the normal to the orbit of the inner orbit and the total angular momentum. And this is the angle that I'm going to play with for at least the 10 more minutes. And I'm going to steal the word prograde and retrograde from observers. So whenever I'm going to talk about prograde orbit, it will be for inclination, this angle below 90 degrees. And whenever I'm going to talk about retrograde orbit, it's going to be for inclinations above 90 degrees. I'm going to do one more thing. So we have total angular momentum conservation in this system. So I'm going to put the z-axis along this vector, along the total angular momentum, because the total angular momentum will not move around. So this is the natural choice of frame of reference. Okay, so I have three body system, and I want to form a stable configuration. One way to do this is to take two of the three body and put them very close together on a tight configuration, and then to put this guy far away. And if I put this guy far enough, and how far is enough we can discuss later, but if I put this guy far enough, this system is stable. And on short time scales, all that will happen is that these two will move around their mutual center of mass, and then these two with that guy will move around the mutual center of mass. And that's it. So I can basically reduce the problem from three body to two wires. So I'm going to smash the masses around the orbit, because again, nothing happened on short time scales. So I'm going to smash the masses around the orbit. In other words, I'm going to average over the phase. I'm going to average over where the object is in its orbit. And I'm going to treat the problem, instead of three body, as two wires interacting with each other. Basically, what I'm saying is that the energy of each wire is conserved, and everything that will happen will come from transferring angular momentum between these two orbits. This problem has already been done. It's been done in the 60s by Lidov, who came first, and then Kozai. Kozai was here, actually, when he did this. And the idea was as follows. Kozai said, well, you know what? I will take the three-body Hamiltonian, I'll expand it in semi-major axis ratio, and I'll see what happened. I'll average over the orbits. And indeed, he did this. And for an orbit that starts out inclined, and by inclined I mean about 40 degrees, and we'll talk later why 40. For an orbit that starts out inclined, this is what he saw. He saw that the eccentricity and inclination oscillates. So when it's less inclined, and 40 for me will be less inclined, it's eccentric. And when it's more inclined, it's pretty much circular, and vice versa. It goes back and forth. He also found this. He found that the z component of the angular momentum, so this is the projection of the inner orbit on the total angular momentum, he found that it's constant. And we can write this, it's 1 minus eccentricity squared times cosine I, and this is constant. And of course it means that if I started with prograde orbit, I cannot become retrograde, because I cannot change the sign of the cosine. So, have I wasted your time? Well, no. Try not to waste time. Anyway, what I'm going to show you is that this conservation law is not conserved in most cases, only in a very specific case. So we're going to have a short, semi-technical part now. It's not going to be too long. I'm going to add a few vectors, and I'm going to see what Kozai had found. And then it's very easily going to be shown that this is not constant. All right. So here is our system. Remember, I've reduced the three-body problem to two wires interacting with each other. Wire 1, the inner wire, and wire 2, the outer wire. And on the 0th order of approximation, each wire is simply a Keplerian orbit. So we have simply two Kepler problems. And Kepler problem, just to remind you, I can describe in 6 parameters. It can be x, y, z, vx, vy, vz. And I'm going to choose angles and momenta, and angular momenta, because I'm talking about angular momentum here. So here are the angular momentum of the orbit, of orbit 1 and orbit 2. And this is the vectorial representation. This is the outer orbit, and this is the inner orbit. I can write angular momentum like this, like 1 minus eccentricity squared. So an orbit which is very radial has very low angular momentum. This makes sense. And now, Sorry. Now I'm going to do something very easy. I'm going to add the vectors. So we're going to move the blue vector around, and we can just write L dot equals to L1 plus L2. Again, very simple. And I want to define the inclinations. Oh, I'm so sorry. This is the total angular momentum. And as I said, this is along the z-axis. So I'm putting the z-axis along the total angular momentum. I'm defining the inclination, so I have inclination with respect between the total angular momentum and the inner orbit, and this is simply I1, and also the inclination between L2 and L dot. So now, before I said that because I found z component blah blah blah, now we can see it. It's much more easier. So the z component of the angular momentum of the inner orbit is simply the projection of this guy on the total angular momentum. Here it is. This is the purple. So we're going to have color coding here, very simple, and it's going to follow us in the next few minutes. And we can do the same also for the outer orbit, and it's simply the angular momentum times cosine I, and that's it. So again, the same for the outer orbit angular momentum z component. So let's go back to this vector, to this equation, sorry. I'm going to rearrange it. I'm going to write, again, only this equation. I'm going to write it in a way that I want it to be written, and then we're going to see what Kozai did. So here it is. I'm going to rearrange it. So I moved L1 to this side, and I wrote L2 equals to L dot minus L1. So just easy. And then I'm going to take the square of it. So this is also simple. This is L2 square equals to L dot square plus L1 square minus 2 L dot L1 cosine I1. We know what this guy is. This is the z component of the angular momentum. We just met him. That's good. All right. Now let's see. What did Kozai say? This is Kozai from a couple of years ago. Yoshida Kozai. And when he was much, much younger, during the 60s, he was here. And this is you see, this is the SAO connection. And he wrote his famous paper here. And what he did was, it's really an amazing work. He took the Hamiltonian of the three-body problem and expanded in semi-major axis ratio to the power of 4. So I'm going to present today something to the power of 3. Just imagine to the power of 4 doing with pen and paper. And then he smashed the bodies around, so basically averaged the two orbits. And only then he truncated to the lowest order of approximation, which is called the quadrupole. And then he applied it for an asteroid in our own solar system being perturbed by Jupiter. And what he found is the following. He found to the quadrupole order, so I'm going to be fixed to the quadrupole order, even though I don't like this order. But it's much easier to show what I want to show you guys on this level of approximation. So again, the quadrupole order is the semi-major axis ratio to the power of 2. So he found to the quadrupole order that the outer orbit angular momentum is conserved. L2 is constant. This means that I have some symmetry for rotation of the orbit of the outer orbit. So for the rotation of the outer orbit. So if it's facing this way or this way, it doesn't really matter. And this is an artifact of this approximation, and this is why I don't like this level of approximation. In the higher orders, the octopole and the, I don't know how to pronounce the next in line, they doesn't happen. But it does, it's been called the happy coincidence by Lidov and Ziglin. I don't know if it's happy, but again, whatever. And then he also found that the z component of the angular momentum of the inner orbit and the outer orbit are also conserved. These are these guys. These are the so-called Kozai integral of motions. This is what I'm going to address and say that these are actually not conserved. And he, in fact, found that the only thing that is varying in time is the angular momentum of the inner orbit. This guy. This is the only thing that is not constant. So let me just remind you Hamiltonian formalism. In Hamiltonian formalism, if I don't see the angle or the coordinate in the Hamiltonian, it means that the conjugate momentum is conserved. And this is because we do d Hamiltonian d coordinate and find that this is how the momentum changes in time. So if I don't have the coordinate, it's simply 0, the momentum is conserved. So in other words, Kozai didn't see any of the angles associated with these guys, and he only saw the angle that's associated with the angular momentum of the inner orbit. This angle is called the argument of periaps. It doesn't matter exactly what the name. And it's in the plane of the ellipse, tells me where the ellipse points at. And people usually like to denote it as little omega. And it's little omega 1, and you see the color code, because it goes with this guy. And that's it. So this is what he found. And this is all we need to see the problem. I want to go back to this equation. All I did in this equation is adding vectors, right? So I don't know how many of you already see it, but let's see. I'm going to mark here on this equation what are the constants here. So first of all, total angular momentum is conserved. There's nothing that will destroy a total angular momentum conservation in the problem. The second thing is this happy coincidence. So again, this is an artifact of the of this quadruple approximation. But still, even if the quadruple approximation is valid, I have done nothing here than add vectors. Another thing that is conserved is the z component of the angular momentum. This is what Kozai found. So do you see the problem? I have red equal to something which is not red, or in other words, something which varies with time equal to something which is constant with time. So we have a problem here. And what happened? So to cut a long technical story short, what was wrong is that there were missing two angles from the Hamiltonian. The angles that are associated with these guys. These guys have angles that describe the 3D tilt, the outside of the plane of the ellipse. So if this is my ellipse, and this is some frame of reference, I have an angle that tells me how this tilt in this direction. And we call it longitude of ascending nodes. Again, it doesn't matter exactly what's the name, but we denote it as big omega. So this is how the Hamiltonian actually looks like. We have little omega 1, but then we have big omega 1 associated with the z component of the inner orbit, and minus big omega 2 associated with the z component of the outer orbit. And if we have total angular momentum conservation in the system, the difference between these two is always pi. Fine, so what? I cannot put the pi in and just ignore it. This is a big no-no in Hamiltonian formalism. This is very similar to do this. I don't know if people here can see it because of, so I'll describe, because of the podium. So this is very similar on taking df dx, evaluated at x equal 2, and put the x equal 2 before doing the derivative. And then I'll get 0. And why is it equivalent? Because what they have done was saying, okay, I want to know if this guy is constant, I'll do dh, d big omega 1, to see if it's constant. And because they put the pi in, they just missed it. But how do they know that it's equal to pi? Well, either they have solved the equations of motion correctly for the Hamiltonian and found that there is total angular momentum conservation in the system, or what usually people do is saying, I'm a physicist, I know that there is total angular momentum conservation in the system, therefore it's supposed to be pi, and let's put it in. Now, it's not really fair. That problem was very, very complicated. And this process of eliminating the nodes, and this is how it's called, elimination of the nodes, was done many, many times before. And it's still very useful because it makes your life very easy. Just as long as you remember to carry this, to remember that you had done some elimination at one point, and you need to consider it when you do the derivatives. So that was done with the technical part. So basically, it means that L sub 1 is not constant, L sub 2z is not constant, so we can eliminate it here, and then this equation makes sense. This z component of the angular momentum is only true in one very specific regime. Only if one of my inner if only one of my inner orbits is a test particle, and if my outer orbit is axisymmetric, for example, if it's circular and I have a test particle, this is the only thing that will be conserved in my system, and that's it. And then it's fine. And a side note, even though Kozai did all of this and implemented the elimination of the nodes, blah, 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 at the end, in his application, he assumed that Jupiter is circular. He had a test particle, which was the asteroid, and that's it. So in his realm of application, he did a fine job. That's interesting. So what did we do? So we allowed the z component to the z component of the angular momentum to vary in time and in magnitude, of course. We also went beyond the quadruple approximation. So I mentioned that I don't like the quadruple approximation because of this happy coincidence. Going beyond this, then we get rid of this fake integral of motion, and then it's fine. And I want to stress that the equations and development of the octupole approximation has been done way, way before us. And basically what it means is that starting from below 90 degrees, we can go above 90 degrees. So saying that we can do this, it doesn't really mean that we can. So can we? Can we flip a planet? So yes, we can. This is one way. This is another. So here I'm showing an example. And this example is for some specific system. And I'm showing here the inclination. The eccentricity is 1 minus e because we always care about the pericenter passage. I'm also showing, just to make a point, the z component of the angular momentum of the inner orbit and the outer orbit as a function of time. So we see here the oscillations between inclination and eccentricity, just as Kozai said that there should be, but we also see that the inclination go from prograde to retrograde, to prograde to retrograde, and vice versa. And we can also see that the eccentricity does something very funny. It goes to a very extreme values. Just for comparison, to make a point, this is what happened if you just use the nominal Kozai. So Kozai, this is the blue. So just compare the blue and the red. There are completely qualitative differences in how the system actually behaves. Okay, I want to show you another example, and the reason that I want to show you this example is, apart from the fact that everything here is really interesting, is that this example, and again, the red is the octupole, the blue is the quadruple. I want to show you that this system we cannot really define a time scale for the octupole, although we dare to do it, but it's still not really definable, and because the octupole produces chaos to the system. So now the system is chaotic, as you would actually expect from a three-body system. And I also want to point out these very high eccentricity peaks. That means that the planet will spend a lot of time around the star. So tides should play a role. So we also included tides into the problem. And here is an example of a planet with octupole, with GR, with tides. And I guess it was written before, but Avi and I and Bense have worked on including GR to this system, which was a very interesting study, at least for me. I don't know with the rest of the world. But anyway, so here we see again the oscillation. Sometimes my jokes are really not funny. So we see again the oscillations between the inclination and eccentricity. And again, green is the quadrupole, red is the octupole. And here I'm showing a zoom in on the last 1, 2, 3, 4 Kozai cycles, the 4 last cycles. And we see that something happened here, and to know what happened, I want to show what the semi-major axis is doing. So here is the semi-major axis as a function of time. This is, again, the zoom in. This is the linear scale. This is the log scale. In red, it's the semi-major axis of the inner orbit, the outer orbit. And in gray is the apo and the pericenter, so the closest approach and the furthest most approach, I guess, however you pronounce it. And you can see that the semi-major axis is constant, and then it drops. We can see it here. There was a very short pericenter passage. We dropped in a step, and then we dropped here. And although it looks like 0 in the linear scale, it's actually 0.0 O2 AU. So I formed a hot Jupiter, and if you look here, I formed a retrograde hot Jupiter, at least in sense of the inclination angle. That's good. But now what about the spin orbit angle? That's also easy. Right? This is an easy problem. I have a top on top of a top, and I actually also have the top of the planet. So I have a top which is the star, around another top which is the orbit itself. So we can solve this, and we have, so this is with the spin orbit angle, how the angle between the spin axis and the normal to the orbit behaves. And this is here, and you can see, yep, so I formed a hot Jupiter, retrograde in inclination sense, retrograde in spin orbit angle, and that's fine. And this is just the entire behavior just to make a point. Okay, so that's good, but maybe I worked for hours trying to produce this, this very fine plot. So we need to actually look at some Monte Carlo, and what we have done is we looked at all kind of things, but one of the things that I want to show you is in a binary situation. And this is because if I have stellar binaries, I can at least have some handle on what the stellar binaries do from observations. So I can take from observations their semi-major axis ratio distribution, their eccentricity distribution, and that will be good. So this is what we have done. We took that from observation. We assumed that the planet was initially aligned, so the spin orbit angle was aligned with the star, with the host star, and the inclination, since we don't know actually anything, we just assume isotropic distribution. And this has already been done in the literature. It was done, although, with a previous Kozai, what is actually, as I explained, is the test particle. It's the test particle quadrupole Kozai, and it has been done. This also should be underlined, and by Dan Fabricki, who is a postdoc here. And what you can see is that they actually predicted the existence of retrograde planets, which is pretty amazing. So there was a prediction even before any were observed. That was pretty nice. But now doing this with the octopole that we saw that works, that describes better the behavior, we get an interesting spin orbit angle. So it's nicer than before, but this is not enough. I want to compare this specifically to observations. So what we have done, we took the different, by the way, the different lines here represent different type of models for what people say about how eccentricity of stars behave, and so on and so on, and tides that we took into account. You can see that mostly it's fine. And so we took this and projected. So we said, what if we were observers, how this spin orbit angle would look? And we compared it to observations and asked, what is the fraction of hot Jupiters produced by stellar binaries by the Kozai mechanism? So the rough answer is 30%, and this is the projected. So this is the green line is our projected spin orbit angle distribution. So this is the distribution. This is the projected spin orbit angle. The black is the observation accordingly to 2012. So it's a bit outdated. And we also compare this to planet-planet scattering. So remember the very first plot that I showed you from planet-planet scattering. And we did a Bayesian analysis. And you can see a few things. You can see that the lines, the shape of the lines are roughly the same with this. But you can see that both of the dynamical mechanisms miss something here. So maybe there is another mechanism, such as maybe planet migration, that make a huge effect. So we also asked the following question. We asked, okay, given this, if we look only on the misaligned systems, because my mechanism can mainly produce misalignment. So if we look only on the misalignment, how much of the misaligned systems are produced through the Kozai mechanism, the eccentric Kozai, or whatever you want to call it? And we found that between 60 to 80%, which is very nice. I want to mention that the idea to do this came from a nice paper from John Johnson with his student Tim Morton in 2011. they have done this using the previous results of the Kozai, and we have now updated this with our new results. Do I have, how many more minutes do I have? Oh, fine. Okay. So have you noticed that we're already in the FAQs part of the talk? So I have more frequently asked questions that sometimes I ask myself. Yes.
One frequently asked question.
Yes.
Are you saying that the green curve is better than the red?
Yes. Yes.
This could explain why that is.
This is from the Bayesian analysis. This is just a projection. If I'll show maps of Bayesian analysis, I'll make everyone fall asleep, including probably myself.
But Bayes says the green is better than red?
Yes.
Compared to observation?
Yeah. So what we said is we have three components here. We have a component which is unknown. We have our component and Nagasawa et al. Component, and we need to compare both the shape and the slope. So this is what we got.
Well, that means that it's a mixture of all of those processes that gives the best fit, not the green over the red.
No, so it means that the green gives about 30% for everything. The red gives about 10% for everything. So if you want to account what happened, this is a bad result. It means 50-50. This is a really bad result. It means that we don't know anything.
But you're not saying that the green has a better fit to the black.
No, we
Red,
said that
you're just saying that more-
we say that the green contributes more
Yes.
compared to the red. Contributes to the black. All right. So and of course I want to say that the 30% result is also consistent with Becky Dawson's work with Ruth Mary Clay, that they did an independent work just trying to figure out what is the fraction of planets that come in high eccentricity like Kozai migration from Kepler results. Okay, one of the frequently asked questions that I get is, why is this angle? Why we have this angle between 40 and 140 degrees? And I'm going to run through this pretty quick. So I said that you need to be inclined, and I kind of glossed over it, and I didn't explain why. So let's explain it. So this is actually, the best way to explain it is to think about a pendulum. So here is a pendulum. This is the equation for a pendulum, a full pendulum, not just small angles. And this is what happens if I just start with a little tilt. You see it moves around, and the momentum and the angle, you see there, I can plot this in this way. This is what happens if I have even a bigger angle and even a bigger angle. I know it's a bit hypnotized. And this is what happens if I give it huge angles. So it goes, you can see that the curve of the phase space of momentum and angle change. And basically we have two behaviors. One behavior which is called rotation or circularization. It represents this. And one behavior which called liberation. So, libration, where the angle is confined to some value. And between them both there is the separatrix that separate between these two behaviors. So this is very nice for a pendulum, but if I want to apply this to another Hamiltonian formalism like the Kozai, it's much more messier. It's even not representative by double pendulum. But we can do something similar. So if we start with a circular orbit and some inclination, we can plot something similar to this phase space. But this is a paper I've done with Yoram Lithwick. And what we can see here is the cosine of the inclination, the eccentricity, and the angle. And the takeaway message of this very busy plot is that the separatrix in this complicated, more complicated system is associated with the 40 degrees and 140 degrees. So now we understand where this 40 and 140 degrees come from. But then the question is, does it hold? Let's see if I'll jump right. No, I jumped wrong. Well, it does not hold. And this is a great project that Gonsia Lee had done. And she did an amazing job. And the idea is that, no, it does not. It's not the end. 40 and 140 degrees do not describe in the end. And what she showed in this paper, now accepted the objet, and this paper that she just submitted, that if you start with low enough inclination, but eccentric outer perturber, you can in fact flip the orbit. It rolls over, which is pretty cool. So you start with low inclination, and then you go just almost straightly to 180 and back and forth and back. You can see that the eccentricity behaves differently than before. And this happens because of those, because of the octopole. The octopole presents a higher order of resonances that produce this beautiful, behavior. I have a confession to make before I'll finish. My confession is that lately I've been seeing triples everywhere. So this has become a problem. I see that triples are important in everything, and they even can get you to the moon sometimes. Well, this is part of the triples that I see, but I also see other triples. So apparently I wasn't the only one, because Matt, of course, started seeing triples before me, I guess. Or at least once, I don't know. But as I showed you now in my talk, I think that I've convinced you that triples are important, at least to understand hot Jupiters, if not even to different applications in exoplanets. Because these are just 3 bodies, and we found such rich and interesting phenomena. Adding more bodies, we can build upon the intuition that we've just acquired and try to understand what happened when you have more bodies in the system. I also see triples in our solar system. Again, I wasn't the first, because I was the first. But here is, for example, a Kuiper belt binary being affected by, this is, of course, not to scale, by our sun. This is not, of course, a representation of our sun. And there is, of course, triple stars. Again, this has been around for a long time, dating up to Harrington, which is the first guy who actually did the octopole approximation for stars, which is very interesting. And it has been shown that they may play a very important role for blue stragglers, for example, and maybe to X-ray binaries. But Josh Greenlee over there, and also maybe very lately got a lot of attention in the literature, maybe also for type 1a supernovae. They also play an important role for black hole systems. So they're all kind of black hole systems, so I was lazy with the photos. So basically what I wanted to tell is that, in fact, what I've just described is applicable in many, many astrophysical systems. And it has been proven, and I think it will be also very, very useful to apply and to gain a lot of understandings. So just to sum up, I showed you that there is a correction to the nominal Kozai formalism. And when we add this correction, we have very interesting behaviors and produce flips and very high eccentricities in the system. I showed you that if we add an additional body in a planet, we can create hot Jupiters, and these secular interactions may play a very, very important role in understanding what's going on. And last, I think that this is a very interesting field, and there are many other applications for different astrophysical settings. And thank you.
Thank you very much. So we have time for some questions. John.
How often does the eccentricity get so high that the planet just plunges into the star?
Oh, that is an excellent question, and it's an excellent because it's something that Gonsia had worked on. And so this is a part of what she had done. So what she did, she mapped, this is a project with Matt and with Avi, and Gonsia had led this. And what we see here, we see what is called surface of sections. This is a two-dimensional representation of okay, I don't want to get too much into this. But the takeaway message from here is that you can have very high eccentricity. So this is eccentricity, and this is the angle, the argument of periapse. And you can have very high eccentricities as a function of your initial conditions. And she had mapped it and asked, what are the initial conditions that we start with, and what will be the maximum eccentricity that you get in the end. It's hard to quantify it, so we cannot quantify exactly what will be the maximum because there is, as you can see here, it can be very chaotic in some of the cases. In some of the cases, it's not. So this is a good question, which we have partial answers for.
But it can happen.
Oh yeah, very, very frequently, yeah.
Sean.
So if you take the population of stars with hot Jupiter, what's known about stellar companions to those hot Jupiters, and can you say anything about the fraction of hot Jupiters that must have if they don't have a body or companion, must have a massive planetary companion and larger radii?
So this is a very good question. So there are two parts of this question. One question is, what do we know from observations? Not a lot. We have very little, maybe a few. I don't know exactly the exact number. I looked at it actually yesterday, and I did the binary flag, and it was so poor and disappointing that I was extremely disappointed. But fine. So it's not enough. We don't have enough observations around. And from theory, we can say that yes, it can either be a star or a planet. So we cannot definitely say, but we can say that you need a companion. So at least from the entire population, at least 30% should have some sort of a companion. For the misaligned population, about 60% to 80% should have some sort of a companion.
Roseanne.
It seems as if these results have such broad applicability that the whole question of stability of planetary systems comes into question. So it sounds as if some systems that we think of as stable may very well not be over the long term. So I'm wondering, this seems to depend on your initial conditions. What do you think about this?
So this is excellent. So there are two ways to define stability. In this work, we have used the hierarchical configuration, right? We have put this guy very far. And I said that how much is far enough? And enough is that the semi-major axis ratio between the two orbits times some function of the eccentricity of the outer orbit will be a very small parameter. So this is one point of eccentricity, of stability. That this orbit will not intersect with this orbit and will not do a scattering behavior. But there is another point for stability. I get that this guy will have very high eccentricity. And when it has a very high eccentricity, sometimes tides cannot react fast enough. And what will happen, I'm just taking a hot Jupiter and throwing it to the star. And therefore, I can, in fact, disrupt many stars. And that has been noted in that paper that I talked about when I did the Bayesian analysis. And in fact, I had only 15% that survived out of it was 25 or 30. So about half died, approximately, from those that had some interesting behavior. And Gonzia, did she leave?
She left.
Unbelievable.
She knows what you're talking about.
Yes. But Gonzia, in her paper with me, with Avi, and with Benze, also quantified this, going in a very nice. She did a very nice grid where she wanted to know what will be the maximum eccentricity that you can reach, or below some limit, maybe probably we're limited by our numerical code. But in that case, what she showed is that you can get to very, very high eccentricities, and then it depends on the times, how fast enough they can work. So you can even many times just take a planet and throw it directly into the sun.
So I think, from looking at your figures, the transition from prograde to retrograde only occurs at very high eccentricity, but that not all very high eccentricity events produce a transition. Is that true?
Yeah, so it happens when you have high eccentricity for the outer guy. You can start circular, actually preferable if you start circular, but it doesn't really matter, because if you don't, you just move the resonance around, so it's fine. So inner orbit will start circular as we want, and then the outer orbit will be eccentric. And how eccentric? It depends on this little parameter that so I can play with this parameter with eccentricity, and then that's fine. So in stars, for example, according to Raghuvahan, probably mispronounced his name, 2010, the eccentricity distribution of stars is in fact uniform. So, that's fine. So I have enough eccentricity to work with.
John, do you have another question?
I was just going to add that there's another Harvard connection that can help you with that binary rate aspect, and that's Heather Knudsen at Caltech is carrying out a
Oh yeah, actually,
wavelength campaign to look for all of those binary.
Yes. So Heather had a nice paper, and in her paper, what she found is that about 50% of all hot Jupiters should have a companion somewhere beyond 20 AUs. So this is her result, which is very consistent with what we find. So that's pretty cool.
Well, let's thank our speaker again.